Alright, assalamu alaikum guys, welcome back. So we're continuing with modulus arguments. So with mod-arg, modulus argument questions, we've got some identities or properties or rules, you could say, that we need to be aware of. And they're right in front of you on your screen. These are just some basic properties involving modulus and argument. So we're going to observe one by one and see how we can utilize them when we're doing our problem solving with complex numbers, and we'll see this through some examples. But real quick, let's start off with the product rules, and this is not to be confused with the product rule from advanced maths involving calculus. It's just this is how the products work in complex numbers. So the first thing we've got here, if we take the modulus of z1 times z2, then it's the same as taking the modulus of z1 times the modulus of z2. And I'm sure you can see the difference there. But all it does, this is just telling you you're allowed to split your modulus if you've got a product, and vice versa of two complex numbers. Okay, now over here, we have the argument of z1 times z2 is the same as argument of z1 plus the argument of z2. So this one is a bit more unique. And you may notice that it resembles a topic you have covered in the past, and that topic being logarithms. Okay, so it's a good way to help you to memorize it. It highly resembles the manner in which logarithms deals with products inside of a logarithm. If I have two complex numbers multiplying, then it's the same as adding their arguments. So if we quickly recall, the argument refers to the angle. So the angle of the first complex number, if a complex number is multiplying with another complex number, then the resulting argument is the same as adding the argument of each complex number. If that statement didn't make sense, then we will observe it through some examples in a minute. Okay, but basically, if I multiply two complex numbers, their angles add. All right, so now the quotient rules. So it works very similar to the multiplication or the product rules. If I have z1, the modulus of z1 over z2, then this is equal to the modulus of z1 divided by the modulus of z2. Okay, so these ones are fairly straightforward. I don't think anyone will have any issues understanding that. But now, the argument of z1 over z2 is equal to the argument of z1 minus the argument of z2. And again, this is resembling the logarithmic behavior when I have the logarithm of two results dividing each other. Then it's the same as subtracting the log of the numerator and the denominator. So it works in a very similar manner. Now, how do we interpret this? Well, if I divide a complex number z1 by a complex number z2, then the resulting angle or the resulting argument will be the angle of z1 minus the angle of z2. Okay, so that's another way to help you to understand that. All right, moving on to the index rules. Taking the modulus of z to the power of n is equal to the modulus of z to the power of n. Okay, so you can see that it behaves almost like normal indices. You can take the power inside the bracket and outside the bracket. Works in a very similar manner. And now the argument, once again, behaves just like the logarithmic results when you have an index inside of the logarithm. You can pop it out to the front just like that. Okay, but basically that means if a complex number is powered by n, then it's the same as taking the argument of that complex number and just multiplying it by n. So basically, the angle of z to the power of n is the same as multiplying that angle by n. You'll get the same angle. All right, and finally the conjugate rules. So conjugates, if I add the conjugate of z1 to the conjugate of z2, that's the same as adding z1 and z2 and then taking its conjugate. Okay, and similarly, the conjugate of z1 times the conjugate of z2 is the same as taking z1 times z2 and then taking that answer's conjugate. Now, all of these identities can be proved, and you can prove them in your own time, and it is highly recommended that you carry out all of these proofs as an exercise in your own time. Just let z equal to x plus iy or r cis theta, depending on the type of question. And I guarantee you can prove every single one of these identities. All right, so now let's start looking at examples and utilize these results. Firstly, we need to borrow some techniques from the previous lesson. So the modulus and argument of z1. Okay, so z1, we want to find the distance from the origin. So that's going to be the square root of 1 squared plus negative 1 squared equals to the square root of 2. And then, actually, I should do it here. I need some space to do this. So we're doing A. And then if we look at the argument of z1, mind you, I should write this a bit more correctly. This is mod z1. So the modulus of z1 is root 2. The argument of z1, if you notice, this is 1, negative 1. If we think about the coordinate, 1, negative 1. On our diagram, it would be here. So it's going to be down here. And if you recall, with all those quadrants, this is going to be a negative theta situation. Okay? So all I have to do is take the tan inverse of the absolute values of that. So 1 over 1. And put a negative out the front. And that'll be enough. So this results in negative pi and 4. So look at that. I know my complex number in its entirety now. So therefore, for part A, I can say z1 equals to the square root of 2 cis negative pi and 4. And if you recall, cis is the short way of writing cos plus I sine theta. And there we go. Hopefully that's clear to everyone. Let's move on to B. We will take the modulus of z2 first. So the modulus of z2 is 1 squared plus root 3 squared. Remember, we just ignore the negatives, although I did write about you can ignore it. And now the argument of z2. So let's observe. This complex number is negative 1 root 3. If we were to observe, this would be negative 1 root 3. So negative 1 root 3. So it's up here in this quadrant. So this means it's actually an obtuse angle. So 180 minus theta, or pi minus theta in this case. So when I do the tan inverse of this, I'll do pi minus tan inverse of, and then just do rise over 1 as normal. So root 3 over 1. Don't worry about the negative. The negative is already taken care of. Okay, and as we can see here, we're going to get pi minus, what is that? Pi minus pi on 3. Pi minus pi on 3, which equals to 2 pi on 3. And therefore with that, z2 or z2 is equal to sorry guys, 2 cis 2 pi and 3. And you can see it makes sense. Length of 2, angle of 2 pi and 3. And you saw the way I roughly plotted the coordinates earlier. It seems to match up. Okay, and now part C. We want z1, z2 in mod-arg form. So z1, z2 is essentially 1 minus I dot, or times negative 1 plus I root 3. But now, because we've expressed them in modulus argument form, we're going to do a shortcut here. And we're going to utilize these rules here, more specifically here. So this means we will get root 2 cis negative pi and 4 times 2 cis 2 pi and 3. I just need to create a little bit of space here. All right, so with that, focusing here. Now, if we look, it tells us that the product rule, we can just multiply the modulus together. So we can see the modulus are root 2 and 2. So this will just become 2 root 2. We'll write cis. Now look at the argument. It tells us if we multiply two complex numbers, then the arguments will actually add. All right, and that makes things so much easier. That means I'm going to add negative pi and 4 and 2 pi and 3. And then I simplify the argument, and that is it. This is such an effective and quick way to calculate these types of results. This one will get negative pi and 12. And that's that. All right, so hopefully there were no issues there. Let's look at the next question. If z1 equals 1 plus I and z3 equals root 3 take away I, find the modulus and argument of z1. So let's start with that. A. Modulus and argument of z1. So we go mod z1 equals square root 1 squared plus 1 squared, which is square root 2. The argument of z1 is tan inverse of 1 on 1. Notice they're both positive, so it's in the first quadrant. I don't need to do anything except just take the tan inverse of their values. And therefore, with that, we have square root 2 cis pi and 4. It's all you need from a complex number. You just need its modulus and its conjugate, and you can express it in polar form with no worries. All right, B. The modulus and argument of z2. So mod of z2 is the square root of square root 3 squared plus negative 1 squared. We simplify that, we're going to get 2. The argument of z2 equals, now real quickly, do a quick sketch of where it will be. So it's root 3 negative 1, so root 3 negative 1, meaning down here, meaning it's just a negative acute angle. If it's negative and acute, it's just negative theta. So all I have to do is negative of tan inverse of the positive values of 1 over root 3. We don't write negative 1. That's taken care of by this, or the fact that it's in this quadrant here. Okay, so now we've got that. This will be negative pi and 6. So therefore, 2 cis negative pi and 6 will be z2. All right, let me just fix something up. z1 equals z2 equals. And then finally part C. Express z1 over z2 in mod-arg form. So z1 over z2 equals, and we just take our two complex numbers. We have root 2 cis pi and 4 over 2 cis negative pi and 6. Alright, so root 2 over 2 is understandable. Now the cis part, this is where it becomes excellent. So when we divide two complex numbers and we know their arguments, then we know that their arguments will actually subtract. So it's going to be pi and 4 take away negative pi and 6. Just like that. Okay. And then we get, when we simplify this, we get root 2 over 2 cis 5 pi on 12. And that's that. So hopefully all is clear on how to create your complex number. Moving on, we've got the next phase. We're going to express 3 plus I root 3 in mod-arg form first. So 3 plus I root 3, the modulus of 3 plus I root 3 is going to be, oh, it's equal to z, so I can actually write z. Z equals to, oh sorry, mod z equals to 3 squared plus root 3 squared, which is 9 plus 3, which is square root of 12. Simplifying that, we get 2 root 3. And the argument of z equals root 3 over 3. Oh, whoops, not. The tan inverse of root 3 over 3. Now, this is in the first quadrant, 3 root 3. So that's why I just took them as both positive. I didn't apply any techniques. And this is actually the rationalized denominator version of 1 over root 3. So the angle will come out as pi and 6. Therefore, z equals to 2 root 3 cis pi on 6. That's part A done. Now part B. Oh, I didn't get it. I should have kept that as 3 plus I root 3. Z itself is actually the whole thing. So a little mistake. Let me just correct it so you understand what I'm talking about, because obviously it doesn't look wrong. And I'm going to correct that. Okay, so it's not Z, it's 3 plus I root 3. We took its mod and we found its argument. And then over here, 3 plus I root 3 equals 2 root 3 cis pi on 6. And there we have it. So now we're going to find Z. So actual Z is Z equals 3 plus I root 3 to the power of 6. So to the power of 6, it's a bit tricky to expand this, but we take this and we make life easy for ourselves. So we get 2 root 3 cis pi on 6, as we've already done all the hard work, to the power of 6. Now you apply power of 6 to the modulus. So that's one of the modulus rules. If you look, we just apply the power. Oh, sorry, this one. We just apply the power. All right, and we get 2 to the power of 6, which is it's actually quite a big number. I'm going to need my calculator for this. So 2 root 3 to the power of 6 is 1728. And here we literally multiply 6 to pi on 6. And as you can see, the 6's will cancel. So really all I'm doing is cis pi. Alright, so this equals Z equals 1728 cis pi. Now this one can be much more simplified. I know we should express it in mod-arg form. That's mod-arg form. I'm just going to take it a step further as a bonus. So let me change the color actually. So as a bonus, this would be 728 cos pi plus I sine pi. Well, if you're aware, you know that sine pi is 0, so there's no imaginary part. But we know that cos pi is -1. So really it's going to be this times -1. So the final answer is -1728. Okay? And that's that. All right, let's move on to the next one. So this is going to cover the fourth example. All right, so here we're doing the modulus of Z1 times Z2. Well, if we use some of the earlier facts, this is the same as doing Z1, or the modulus of Z1 times the modulus of Z2. So let's take that and express it here. All right, so I'm just going to follow that rule from before. I'm going to modulus that, so that's 3 minus 2i. And over here, Z2 is 2 minus 4i, so we're going to do 2 plus 4i. And me expanding this will give me the correct answer. Or if I use mod-arg form, I can do that as well, but I think it's a bit easier in this case. So like this, minus 8 plus 8, 14 plus 8i. And it's done. So instead of expanding it as this first and then taking the conjugate of that, it's just sometimes easier to conjugate both and then do it. Now Z1 plus Z2 is even easier. This is the same as taking the mod of Z1, adding it to the mod of Z2. So 3 minus 2i plus 2 plus 4i. And like I said, you could quickly test these in your own time, or by proving the actual proof. That will make it evident that it does work that way. And there we have it. That's the answer for those. Now, there's a challenge question here. I'd like for you guys to, I'm going to leave it. I'd like for you guys to try it yourselves. I want this result in mod-arg form, but I want you to do it two ways. I want you to do it just normally, and then I want you to do it exclusively using mod-arg form or polar form. So on this side, you'll do Cartesian form, so the easy way. Just multiply these and then take the conjugate of the denominator. So Cartesian method. And then on the other side, I want you to do the polar method. So the method we just learnt. Express each one in cis form. Even if it doesn't have an exact angle, make sure you calculate in radians. I still want you to work it out using polar form. All right, so there's a few questions here. I think we can cover it. I'm going to leave it for now, but this is what we'll be working on in the next video.